Hello. We have talked about voltage or electric potential with units of volts. We talked about electric current with letter capital I in units of amps. And we also said that electric current is the flow of charges in time, or in other words, this is also coulombs per second. We also talked about how power is energy over time. So power has units of watts and energy is units of joules. And power is joules over time. Now we have to talk about one important concept, which is resistance. Resistance is a function of materials. So when you have a material, you can basically, there are three types of groups of materials, which are conductors, semi-conductors, and insulators. Conductors, we have copper, we have gold, we have silver, etc. Semiconductors, we have silicon, it's very famous, and phosphorus. And then insulators, we have um, barium titanate, we have glass, etc. So we are focusing mostly in conductors. When we talked about capacitors, we talk about insulators in a subgroup that is called dielectrics. And semiconductors is more for when we talk about digital circuits, when we need logical gates like transistors and amplifiers. Semiconductors are very useful when it comes to make parts that are active parts. Active parts are amplifiers and transistors, etc. Now, resistance is a property of conducting materials. Well, actually, it's a property of all materials, but resistance is very small for conductors. In fact, the resistance is the inverse of conductance. So when a material is very conductive, has very low resistance. Conductors have very low resistance. Why? Because we want electrons to flow through the wires, through the material, so that we can um, let charges flow. So today we will talk about resistance, which is a property found mostly in high quantities for conductive materials. So the goals are to know how to determine and calculate the resistance of elements and to be able to compute the resistance from a certain dimension or geometry. So in this particular part, when we talk about resistance, we have to take into consideration the length, the diameter, the material. This part is dependent on the geometry and the material. So one of the main goal is to know how to determine the resistance of a material, knowing the geometry and knowing the material. Also, we want to understand the effect of temperature. By now, you'll start noticing that temperature is a very key aspect of how materials behave. In fact, if you take water, low temperatures, you freeze water. At normal temperatures, for ambient temperatures, you have liquid water, and then for hot temperatures, you have vapor water. Something similar happens in metals and non-metals. At some temperatures, the material is very good conductor. At some temperatures, it's very bad conductor. So we want to start noticing the effects of temperature on the resistance of a material. Also, we want to become familiar with a broad range of commercial available resistors and how to read the color code that is printed on that resistor. And lastly, we want to be able to become familiar with elements such as thermistors, photoconductive cells, and how is their resistance controlled. So first of all, we talked about voltage and we talked about electric current. So a resistor or resistance is a very key aspect because when you have electric current flowing through a material, that resistor will determine the voltage potential that you can have through the resistor. This right here is called Ohm's law. Ohm's law. And Ohm's law says that the voltage potential through a conductive element is equal to its resistance times the amount of current that is going through it. This is a very useful law that we'll use. We will use this law every day for this class. Now, if you remember, also we just mentioned that electric charges are the flow, or electric current is the flow of electric charges with time. So when you have electric charges flowing through a given area through time, you have what's called electric current. Now, the voltage is related to the electric charge by something called capacitor. And this is also property of a material. Capacitors are properties of dielectrics or insulators. And we'll talk about those elements later on. In capacitors, you hold charges. You charge up the capacitor because you have no conductivity. It's polarized, it's an insulator, so charges cannot flow. So they will pretty much be saved within the capacitor, and you can use that charge later. Okay, so voltage and electric charge these quantities are related through something called capacitance. The units of capacitance are Farad after Michael Faraday, sorry, and the units. This is International System of Units will tell you that it's basically coulombs squared times seconds squared divided by kilograms per cubic square meters. Okay, so we have charges squared, time squared, mass, and length squared. So it's a lot of quantities related to capacitance. Electric charges, time, mass, in the length or geometrical shape. Now, magnetic flux, which has units of Webers, also units Webers are the same thing as ohms per coulomb, or per coulombs. Yeah, C is the unit of charge, not capacitance. C is coulombs. The units of capacitance is farads, F. So ohms per coulombs is magnetic flux. And you can relate the electric current through the magnetic flux through something called inductors. Okay, inductors have units of henries, capital H, and inductors are basically magnetic flux divided by electric current. The International System of Units will tell you that the units of inductors are ohms per second, or mass, length over charges. And electric charges and magnetic flux are related through something called memristor, or something that can, I don't know if you've heard of this term or seen this term. It's not extremely useful for a lot of commercial applications, but for research is very useful because memristors have resistance. It has memory. Basically, you can tune the resistance based on the inputs that you apply, the currents and the voltages. So memristor has units of coulomb squared per second squared divided by kilograms per meter squared. Okay, so voltage and charges are related to capacitance. Voltage and currents are related to resistors. Current and magnetic flux are related through inductors. And charges and magnetic flux are related through membristors. Notice that all these things are based on materials. So you can have a resistor that is based on carbon. You can have an inductor that is based on copper. You can have a capacitor that is based on barium titanate, and etc. So the physical quantities are related to each other through materials. Also, when we focus about resistance, we have to mention basically the opposition to flow of charges through an electrical circuit is called resistance. So when you have electric charges flowing through your wire and you place a resistor, what is going to happen is that it's going to resist the freely flow of charges through the wire. And this resistance could be very large or it could be pretty small. It could be 10 ohms or it could be 100 mega ohms. Could be different stuff. The symbol is omega, and also the opposition due to the collision and friction between the free electrons and other electrons or ions and atoms in the path of motion converts the supplied electrical energy into heat, and this will rise the temperature. So basically, when you have electric charges going through your copper wire, for instance, if the wire is copper, and you have a resistor, the atoms of the resistor will first of all have different size from the atoms of the wire. So when you have electric charges going through your resistor, you will notice, or basically the concept is that it will impede the flow of electrons because they have to go through this other material that is not as conductive. Okay. Also, when you have resistors in your circuit, since you have resistance, the flow is not able to flow freely, the temperature is gonna increase. Now, here on Earth, you have air and you have fans that you can blow to your circuit. You have air to blow on your circuit so you can cool down the circuit. But for instance, when you go to space, like when astronauts go to space, the circuits, well, you don't have air flowing through your circuit. So what they have to do is you have to have liquid nitrogen below and around the circuits to cool down your circuits, since the temperature of your circuit increases given the resistance of the elements. So I always remember that example from how circuits for spaceships and circuits when you go to space and take a circuit or electronic device, those circuits are not the regular circuits here on Earth. They need a coolant such as liquid nitrogen to cool down the circuit. Now, resistance and resistivity. So resistivity is basically related to resistance. Resistance is the opposition of flow of free electrons. Resistivity is a material property. Okay, so the main factors that affect the resistivity are the type of material, if it's copper, if it's gold, or etc. The length of your wire or your circuit or your material that you want to analyze, the area from the cross section, so this area right here, and the temperature of the material at every instant. Okay, this is because the atomic structure determines how easily the free electrons will pass through a material. So if you remember, gold has a cubic um, configuration of atoms. So atoms can flow freely through gold, but silicon has a very complex diamond shaped structure where atoms cannot flow freely through it. Okay, the longer the path through which the free electron must pass, the greater is the resistance factor. That's why when you have wires for circuits, which we here in US use American gauge, wire gauge, they will tell you different diameters, different gauges, because if the wire is long, the resistance will increase. So we mentioned that different elements have different resistivity. And this is an example. The resistivity of silver is 1.6, is 1.645 times 10 to the negative 6. These units are in ohms per centimeter. Okay, this looks like a very small number, but it is pretty small resistivity, right? This is extremely small. So it's 1000, so it's basically 0.123451645 ohms per centimeter. This is the resistance. It's virtually zero, the resistance of silver. The resistance of copper is 1.723 10 to the negative 6. The resistance of gold is 2.443 10 to the negative 6. All of them are 10 to the negative 6 or micro. 10 to the negative 6 is micro ohms per centimeter. We have aluminum that is 2.8. So they're increasing, right? The least resistive is silver. You have tungsten that is 5.48. Nickel is 7.8. Iron is 2.28. Tantalum is 15.4. Nichrome is 99.72. Tin oxide is 250 and carbon is 3500. That's why if you have a circuit that has wires that are made of copper and you have a resistor which is mostly made of carbon, you have a very low resistance and then it increases basically 3000 times, 3500 times. And then you have resistors made of carbon. This is a huge resistance compared to silver. Another thing is that safety issues are important to consider. If you wear rings or jewelry out of gold and or silver or tungsten, well, or platinum, those are very poor very high conductors. So when you work with with circuits, make sure you remove your rings because you can get electricity going through the ring and then you be in the ground. It could be pretty bad. You can have a lot of current going through your ring if you're not careful. Okay, so we were saying that the conductor has very low resistivity. So copper has 1.723 times to the negative 6 or micro ohms per centimeter. Now, semiconductors, we mentioned some of them. Germanium is 50. Silicon is 200 times 10 to the 3 or 200 kilo ohms per centimeter. So very large resistance. A conductor has very low resistance. A semiconductor has pretty high resistance. Germanium and this is used for gallium arsenide is used for lasers, semiconductors for lasers. This is 7 10 to the 6, so 7 mega ohms per centimeter. Now, an insulator is huge. It's basically not going to let any charge flow through. And this is 10 to the 15. Now, when we talk about temperature effect, we have to understand that temperature can cause a few things. One of them is that when the temperature increases, the coefficient can increase. So that would be the case, for instance, if temperature increases and the conductivity increases, that is called a positive temperature coefficient because both are increasing. As I said, if the temperature increases and the conductivity increases, that's a positive temperature coefficient. For good conductors, an increase in temperature will increase the resistance. Now, a negative temperature coefficient means that if the temperature increases, the temperature coefficient will decrease. So, for example, if temperature decreases and the resistivity decreases, that is a negative coefficient. And for semiconductors and insulators, an increase in temperature will result in a decrease in the resistance. So for instance, if we said that the resistance of silver was 1.6 times to the negative 6, if temperature increases, it will increase the resistance level. So this is a function of temperature. If it increases, it will go up. And we don't want the resistance to go up in a circuit because we want to be more efficient, generate less heat, and be able to flow more electrons through the circuit. So that's why we have to cool down the circuit. And for semiconductors, it's the opposite. An increase in temperature decreases the resistance, which is not what we want. We want to have a high resistance so that the transistors can operate efficiently, only letting the right amount of current to go through so that we can operate with those thresholds as logical inputs, right? So what I mean is, if we have a digital gate where from 0 to 2.5 volts is going to be logic 0, or close a valve, for instance, and from 2.5 to 3.3 is a 1, or open valve, and then we vary the resistance that, say, increases the temperature of the ambient or the circuit, then the resistance is going to increase. So the same amount of current will go through the circuit. The voltage threshold is fixed, but if the resistance changed, now it's going to have errors because now it's not going to be 2.5. Now it's going to be a different, it's going to have a different voltage that is applying, even though it's expecting a 2.5, but before it was at 2.5 at normal temperature conditions. Now it's going to supposedly be a 0, but since the circuit is warm or hot, then it's going to trigger a value that is an error because the resistance changed. And remember that voltage equals resistance times current. So if the resistance increased or decreased, then obviously these values of operation will be changing. Okay? Meaning, for instance, if the resistance was 100 ohms for the circuit and the current was 1 milliamp and the voltage was say 2, okay, so basically now look, it's going to be 2 divided by 100 is going to be 2 milliamps, when before at regular temperature conditions was expecting 1 milliamp. So this is what I mean. The current, sometimes equipment will expect a current value to operate, and sometimes it will be from 0 to 20 millivolts mostly. And so this is a huge error if it is expecting 1 millivolt and instead you give it 2 millivolts. This is pretty bad. This could fail the test. So make sure that you always remember that the temperature is a key aspect. Mostly you must measure temperature of your points of your circuit. Okay, we also talked about the resistor code. One of the goals is to learn or be familiar on how to read the resistor code. And there's a table that this is standardized. This is always going to be like this. And the colors are black, brown, red, orange, yellow, green, blue, purple, gray, white. This will be the color code table. And the multiplier is 1 for black, 10 for brown, 100 for red, all the way to white, okay, which is 1 billion. And the tolerance is also related to the color, okay. So, for instance, for a 4-band resistor, you will have the last band, it's always its tolerance. So it's saying it's gold. When we go here to gold, we see that the tolerance is 5%. So we already know that this resistor is not extremely reliable. This is for a hobbyist or for a, for a circuit that is not very important. Now the 4th band is orange, and that is the multiplier. So orange is 1,000. So we already know that this one will be kilo ohms. with a plus minus 5%. The second band is the second digit, which is black, and black is 0. And the first digit is red, which is the color is 2. So this resistor is 20 kilo ohms with a 5% sensitivity. Okay, the 5-band resistor is the same thing except for the first three colors are the net number, the last two are still the multiplier and the tolerance. So this particular one has the last number is brown, and brown has a multiplier of 1%, so this is a much better resistor. Then has a brown as the multiplier, and brown is also is 10. So we have brown for the sensitivity or the tolerance, and brown for the multiplier. Then we have green, which is the a number. It's going to be 5. Then we have purple, which is 7, and we have blue, which is 6. So this is 675 times 10, so it's 6,750 ohms and a 1% tolerance or sensitivity. This is how you read your resistor value. We also talked about multimeters, and we already know how to measure the voltage and the current with the multimeter. Remember, if you want to measure the voltage, you simply put your multimeter near voltage, DC or AC. DC is a straight line, AC is this little tilde. If you want to measure voltage, you simply place your resistor at the places where you want to measure your potential. If you want to measure current, you have to break in your circuit, remove the wire, and place your multimeter in line with the circuit. But you can also measure the resistance. There's an ohm resistor on the multimeter setting, and what you can do is just basically measure both ends of the resistor, and it will send a current and a voltage fixed, and it will measure the resistance of the value. It will expect a value back, and it will basically say, oh, okay, this is 10 times larger or whatever, so this is the resistance. Basically, you measure the ends of the resistor with a multimeter on the ohm setting, resistance setting, and you can measure the value of the resistor. Now, the other concept is that there's a variable resistor called a potentiometer, and it's very useful because sometimes you have to tune your circuit. So what you do is that you have a range of resistances that you can have back. So there are, 10 to 1,000 ohm resistor, and you basically use the knob to find the value in between that you really want to use for your circuit. So these things potentiometers are great for tuning and designing circuits, because sometimes you need to tune the right amount of threshold or the light bulb current that you want to have. So the concepts are that with your multimeter you can measure voltage, current, resistance, and the potentiometer is basically a variable resistor. And we were saying that temperature resistance, the temperature is a key aspect on the resistance and conductivity in most physical quantities. So we talked about positive coefficients and negative coefficients. Positive coefficients are coefficients when you have temperature increase, your property increases, and negative coefficient means that when you have temperature increase, your variable decreases. So for instance, this is a positive coefficient because we increase temperature and our electrical resistivity increases. And then we have here different alloys or different mixes or solutions of solids. We have copper and nickel, we have copper at different percentage, so the solutions are different percentage. Also, this is what in mechanical engineering is called worked, so cold worked or cast iron. And so depending on the manufacturing process that you follow, you can also have different values of resistivity. So for instance, pure copper, we said it was 1.6, 10 to the negative 6, sort of like right here, 10 to the negative 6, or 10 to the negative 8 ohms per meter, right? Because this is 100. So we're at 2 zeros. And then basically what we're saying is that if you want to have more resistivity, then you can increase the resistivity by mechanically deforming the material or by adding other materials such as nickel at different percentages to create a solid solution. Also, sensing devices using resistivity. This is very useful because we can have sensors that use this concept of if you want a voltage and you want a current to be your value. So, 0 to 5 will basically mean 0 to 100 psi, for instance. So if you have 0 to 100 psi, but you measure 0 to 5 volts, you can have this transfer function. Well, you can have that with a variable resistor, for instance, or a temperature-dependent resistor called a thermistor, right? And this is actually a type of temperature sensor that it will vary its resistance given temperature. And this is the symbol for the thermistor is a resistor with a T and an arrow. And the specific resistance of a thermistor with, depending on the material, but this is just one example. It has a negative temperature coefficient. And even though it's nonlinear, um, you mostly only would care about specific range. So say for instance, between 100 from 0 to 200. And inside a circuit would linearize your circuit. When you buy your sensor, a circuit inside will linearize these values with some error corrections and some filters. Now, a photoresistor is similar. It's basically light will create electric charge, and then depending on the resistance of the type of photoresistor, you can measure the voltage and current across. And you can go from very small resistance from 0.1 kilo ohms to a huge resistance, 100 or 100 kilo ohms. And this is based on the cell resistance in the material used for the photoresistor. And the illumination level is measured in candles, or there are different type of units, but this one is also a negative coefficient. And what it means is that at higher resistance, you have, sorry, you would have larger illumination given the least amount of resistance, right? Makes sense, because you need more charges to go through it. So these are type of resistors that use resistance as its input. There's another type of resistance application with resistors or modified resistors, which is called a variable resistor or varistor. This is used to protect circuits. And this is great because it will be having a very small resistance letting all the current through until it reaches a threshold, and then it will increase its resistance so that it will protect the circuits when there's a huge increase in current. So like if your circuit is rated for less than 1 amp, notice that it will work perfectly fine up until 200 volts. But if for some reason there's a shortcut or whatever, and then the volts increases, if you have a surge of voltage and from 200 you go to 210, then you will basically go high on the current, and you don't want this. So you would have a resistor that basically will shut your circuit at 150 or 200, and if it goes above, then it will shut down your circuit. So this is a non-linear resistor application called a variable resistor or varistor. And notice that a typical resistor is linear. You increase the voltage, you increase the current. So a typical resistor will pretty much at 150 already have 4 amps, but this is not what you want. You want a protective equipment or protective item or something that you can put in your circuit that is not going to affect the performance, but it's going to protect it for high voltages. So as I said, at 200 volts, this varistor will protect the circuit, and it will basically say, oh, okay, at this point we're going to not let any voltage go through. And as we said, memristor is a nice, excellent technology for research because you have a type of resistor that it will pretty much remember the value, the charges. So in fact, a memory resistor in the element itself, the resistance increases with the flow of charges in one direction, but decreases as the flow of charges flows in the opposite direction. So in one direction has high resistance, but in the opposite direction has low resistance. So it acts like a gate. So it's very useful. Okay, so they're very small. This is 15 nanometers, so which is extremely small. This is 50 times 10 to the negative 9. And this image has 17 memristors, right? 1, 2, 3, 4. So they're extremely small, meaning that you can use them in small smartphones and computers. And as I said, it's excellent because you can have current go through one side of the resistor so that you can do your typical applications. But instead of using a diode, you can use the same memristor so that the current wouldn't go in the reverse direction. Because you know, in a resistor, you can place the resistor anyway. It's not positive. Actually, some capacitors are like that too. When you have a resistor, any point you could be positive or negative. It's just something that will impede the flow of current. But with our memristor, it's important to know what direction you're going to apply your current to go through. So you have to know which one is your polarized leg. Now, superconductors are also mainly used in research because they have high values of conductivity. So if you remember, Kelvin is a unit of temperature. So 100 Celsius, which is 212 Fahrenheit, is 373 Kelvin. Okay, 0 Kelvin is basically the measurement of no movement of atoms. So like liquid helium boils at 4 Kelvin. Temperature in space must be very close to 0 Kelvin since there's no air particles bumping and moving. But basically, semiconductors are conductors that have electric charges that have zero resistance. So you know how copper we said is excellent conductor, but still has a resistance in the order of 10 to the negative 6 ohms per centimeter, whereas semiconductors have virtually zero conductivity. Okay, and that also, of course, is a function of temperature. So, what are superconductors? Superconductors are elements with made of metallic alloys, meaning they're a solution of different metals, and have basically they conduct electricity without any resistance, and that happens below a certain temperature. Remember that resistance is not desirable because it produces losses and inefficiencies. Once set in motion, electrical current will flow forever in a closed loop superconductor. So that's why superconductors are so interesting, because you can have electricity flowing forever if you have no resistance to the electric flow, right? If you think of an atom, you have the nucleus and then you have protons and you have electrons going around the atom. Theory says that these electrons will go around forever around the nucleus. So basically there's no resistance in this orbit. So they're superconductors in a sense that the atoms will always be rotating and they will not stop unless you apply some physics to it and you make the atoms like jump to different levels of energy, like in lasers, etc. But the concept of superconductors is that electrons can flow forever. Some materials that are used for research are lead, lanthanum, tantalum, and a combination of them. And they're behaving as superconductors at 7 Kelvin, so very low temperatures. That's like almost negative 300 Fahrenheit. 4 Kelvin and 4.47 Kelvin. Now, latest research that I saw is that this nice molecule solution with barium and all this magnesium and oxygen is acting as a superconductor at a very warm temperature, 216 Celsius. Water boils at 100 Celsius, so this is extremely hot. And of course, this is material science, which is the configuration of the atoms. So this is phase center cubic, this is body center cubic, and so on. So if you're interested, you can look into these elements. So as we said, in non-superconducting materials would increase the resistance with temperature. But superconductor materials would be no resistance until a threshold temperature that will behave like regular conductors. All right, so let's talk about basic elements for power supply. We talked about battery. Also, solar cell is a source of energy. A DC power supply, which you will have to buy an AC outlet from your house or office, which is from your energy company. And then basically you can get either DC or AC power supply, right? So this will give you AC most likely, and these all their three will give you a DC power supply. Equipment for testing are oscilloscopes, very useful for digital and high frequency signals. Multimeters, the probes, both for multimeters and for oscilloscopes. Function generators, so you can test your circuits with different inputs, such as like square waves and saw waves, etc. And frequency counters, extremely useful for digital sensors. So basic components are passive components are resistors, capacitors, transformers, inductors, and crystals. Passive components create passive circuits. So voltage divider is a circuit with with resistors, which have passive components, and we'll talk about voltage dividers later on in coming soon. Filters use capacitors and resistors to filter signals, also using passive components. Active components use op amps and use transistors, and this is basically where the concept electronics comes for active components. And that's what we're saying. Active components will be diodes, transistors, integrated circuits or ICs are processors and microchips. Processors are basically a bunch of diodes, transistors, resistors, capacitors, and inductors in a single circuit. But they're active or smart because they have transistors and amplifiers. Now, for the development of basically the flow of designing a circuit is you start with a drawing or with basically Tinkercad or some software. Then you use a breadboard and you create your prototype. Then you create solder paste. You can solder your stuff into PC boards or printed circuits. Then you can create a 3D printed enclosure or buy a plastic box, and then you can produce your part high volumes inside them. So this is basically how the flow of the circuit goes. Like once you have your product working, you can just make more and make more, like iPhones, that once you have one working, you can make 1,000 and sell them, which is what Apple did. Also, to test your circuit, you can use data loggers and network analyzers, such as the HP 800 series. And altogether, we have input devices such as switches, sensors, keyboards, function generators. Then we're studying the basics and the theory of how they work. Then you can create your analog or digital inputs and outputs using your logic gates or your voltage divider if it's analog versus digital. And then you have your output or resulting signal that you want, if it's an LED display, if it's to operate a motor, if it's a transmit a signal. So transmitting a signal will be through an inductor. So this will be basically electromagnetic waves. DC motor will require actual electromechanical current, and LCD will require photons. And then we talk about one of the main aspects of DC electronics, which is sensors and actuators. So sensors, you can have different types: temperature, motion, proximity, humidity, RPMs, torque, flow, electric field, and they use different um, principles. So for instance, if you want to measure the RPM, you can have a photo effect, a photo resistor that it will measure basically how many times a single point will go through, and then that will be translated to RPM. And if it's not going through, it will be 0. If it goes through, it's a 1. If it doesn't go through, it's a 0. If it goes through, it's a 1. And how many times this happens in a second will give you a frequency that you can translate into radians per second or RPM. So the physical stimuli will happen, and this is what is called a transducer. Transducer will take a physical signal and make it into a electric magnetic signal, and then you would get an analog signal, say a voltage from 0 to 5. Then you have to digitize into zeros and ones, and this is where it becomes a very high precision or high resolution sensor, so you don't miss important events. And then you amplify it with an amplifier, so you can, because these are going to be very small signals like milliamps and millivolts, so you amplify it so you get the 0 to 5 volts from your signal. And the actuator is the opposite. If you give it a 0 to 5 volts, the actuator will open a valve and close a valve 0% at 0 and 100% at 5 volts. So if you give with your computer or with your instruments, you apply a 2.5 volts with a button or with a click or with a knob, 2.5 volts will open a valve 50%. So actuators are the opposite as a sensor, but they have the same principles. Now, when it comes to sensors, there's something called accuracy and precision. So you can have high accuracy, but or you can have high precision but low accuracy. So if you're accurate, you'll be right at the middle. Okay, if you have precision, so basically when you have a sensor is to measure multiple points, not just one. So say if you measure multiple points and they're all over the place, that is a very low precision and low accuracy sensor. If you measure several points and they are more or less around the expected value, they have high accuracy but low precision. Okay, high accuracy is because they're close to each other. If you have all the points very close to the points that you keep measuring, but they're far away from the value that you know is true, then they have high precision but low accuracy. Remember, accuracy is the point that you need to measure that you know is true. Now, if you're right on the point that you know is true, because you're calibrated to that point, and all your points measured are on that same temperature point or same pressure point or whatever, you have high precision and high accuracy. So precision is the number of digits reported by the sensor, or the ability to keep measuring consistently. Now, accuracy is the deviation from a true value, and you know the true value with a calibrated value, right? And the resolution is the scale of quantized value after discretization. So you have a 16-bit sensor versus an 8-bit sensor. Of course, you're going to have much higher resolution with 16 bits.